Hello everyone, so here are your notes for 9.5, the sine and cosine ratios, part 1. So we are now going to go ahead and introduce two more trig ratios to our toolbox. We've covered tangent already in 9.4, now we're going to go ahead and introduce two more. So in right triangle ABC, the sine ratio of angle A is the hypotenuse and the opposite leg. So just similar to tangent, how we use two sides of the right triangle, we also use two sides of the right triangle for sine, but it's a different two sides. So let's go and quickly label our triangle. So side CA is our hypotenuse. The side that is directly opposite of angle theta, or angle A, is going to be my opposite leg. And last but not least, BA is my adjacent leg. So, as an equation, the sine of ratio looks like this. We say sine, but we abbreviate it to SIN. Sine of angle A is equal to the opposite leg divided by the hypotenuse. We can, of course, go ahead and say sine of theta just because there is a theta written there as well, but it will be the same exact ratio. So sine is going to be opposite divided by hypotenuse. No matter what kind of triangle you have, or rather no matter what kind of right triangle you have, we are always going to pick the opposite leg, and the hypotenuse. All right, now the last trig ratio that we want to go ahead and go over is the cosine ratio. The cosine ratio is very similar to sine, except for one difference. So in right triangle ABC, the cosine ratio of angle A is the hypotenuse. So this is where it's the same. And the adjacent leg, though, instead of the opposite. So, same triangle, labeling all three sides with hypotenuse, opposite leg, and adjacent leg. The two sides that we use for cosine of angle A is going to be the adjacent leg divided by the hypotenuse. Again, I can go ahead and rewrite that using theta. So cosine of theta is equal to the adjacent leg divided by the hypotenuse. Here's the adjacent leg. Here is the hypotenuse. All right, now let's go ahead and let's put all three of these ratios together on one page or one screen. All right, so relabeling one more time. I have the hypotenuse, my opposite leg, and my adjacent leg. Now, you may or may not have heard of SO, CA, and TOA. This SO, CA, TOA is an abbreviation. It's an acronym to help us remember all three ratios. And I'll show you what they look like. So let's go ahead and rewrite all three ratios down first, though. So we have sine of angle A is equal to the opposite leg divided by the hypotenuse. We have cosine of angle A is equal to the adjacent leg divided by the hypotenuse. And the one that we learned before is tangent of angle A is equal to the opposite leg divided by the adjacent leg. All right, so here is where SO, CA, and TOA come in. I'm going to take the S from sine, the O from opposite and divide it by the H from hypotenuse. There's our SO. And now I'm going to take the C in cosine, the A in adjacent, divided by the H in hypotenuse. There's our Ka. Last but not least, we have T from tangent, O from opposite, divided by A in adjacent. So this is where we get SO, Ka, and TOA from. Again, this is just a little tool to help you remember which ratio belongs with which trig ratio, right? And then one other thing that I want you to keep in mind is that it can be confusing as to which one do we use. So I'm going to make a note here and then we will refer back to it a little bit later. But which trig ratio you use depends on the given info and what you're solving for. So the two words that I want to highlight is given and solving, because those are the two key pieces of information that we will need and we will use to help us to make the decision of, are we going to use SO, are we going to use Ka, or are we going to use TOA? Let's go ahead and let's start looking at some examples. All right, so here is example 1. They want us to write the trig ratios for sine, cosine, and tangent. So all three ratios. And they want us to do it for both of the acute angles. They need it as a fraction and as a decimal rounded to 4 decimal places. All right, so let's go ahead and let's actually add some labels to our right triangle first. As for the angle, let's go ahead and let's focus on angle Z first, even though we need to do it for both angle Z and angle W. All right, so now that I've labeled angle Z, I need to label hypotenuse, opposite, and adjacent. Hypotenuse is, of course, always across from the right angle. My opposite leg this time is right over here. It is the 2. And the 8 then is my adjacent leg. All right, now, because I need to write all three ratios, though, for sine, cosine, and tangent, in order to be able to fill all those in with values, I need my hypotenuse because they don't give it to us. Now, because this is a right triangle, in order to find the missing side, any of the missing sides on a right triangle, we're going to go ahead and we are going to use the Pythagorean Theorem. All right, so Pythagorean Theorem says a squared plus b squared is equal to c squared. And our variable c is always the hypotenuse. So a squared, I'm going to go ahead and substitute that in as 2 squared plus 8 4b squared. And this is all equal to my hypotenuse squared. 2 squared is 4 plus 8 squared is 64 is equal to c squared. We get 68 is equal to c squared. Now we need to go ahead and square root on both sides of the equation to cancel out my square and my square root. So we now have the square root of 68 is equal to just c. But if I want to go ahead and simplify this square root, I'm going to go and skip right along to say that 2 times the square root of 17 is c. So that's what our hypotenuse is. All right, I'm going to go ahead and leave what we did with the Pythagorean theorem just a little bit smaller over here on the side. Just go ahead and rewind the video if you need to see this a little bit bigger. All right, so now let's actually go ahead and start writing all of our trig ratios for angle Z. So this is where SO, CA, and TOA would come in handy. SO is sine of angle Z, which is the opposite leg divided by the hypotenuse. And because we've labeled our triangle appropriately, it's just a matter of substitution. So sine of angle Z will be equal to 2 divided by 2 times the square root of 17. Cosine of angle Z, which is CAH, C-A-H, the A was for adjacent, divided by H, which was for the hypotenuse. This is equal to 8 for the adjacent leg, divided by 2 times the square root of 17, again for the hypotenuse. All right, and last but not least, we have tangent of angle Z, and this is equal to the opposite leg divided by the adjacent leg. Substituting in, this answer is a little bit cleaner to look at. We got 2 divided by 8. All right, so those are all of our trig ratios for angle Z. Let me go ahead and quickly write in the trig ratios for angle W, and then we'll take a look at it. All right, so over here on the right side, I have the ratios for angle W. The first thing that I actually want to pull your attention to is the fact that our angle that we're given or focused on is angle W. And because my theta is now at angle W, I need to change 8 to be the opposite leg, and now 2 is the adjacent leg. Notice how in sine, I still have opposite divided by hypotenuse, but for sine of angle Z, there was a 2 in the numerator, but for angle W, it is an 8 in the numerator. And so anywhere where we see adjacent and opposite, those two have now been swapped. All right, now we're almost done. We have found all of our trig ratios written as fractions. But the problem still asks us to write these ratios as decimals. So let's go ahead and let's pull up Desmos and do exactly that. Okay, so right down over here, what I've done is I have rewritten our ratios for sine, cosine, and tangent of angle Z. You can, of course, do the same thing for angle W, but we're just going to go ahead and do angle Z, and then I will write the decimals for angle W, and you can double check. All right, so in Desmos, we're going to go ahead and we're going to type 2 divided by 2 times the square root of 17. I'm going to go ahead and hit enter. All right, and this number right here is going to be our ratio as a decimal for sine of angle Z, right? 2 divided by 2 times the square root of 17. So I went ahead and hit 2, and then I hit divided by 2 times the square root of 17. All right. So taking a look at our answer, this is going to be rounded off to 0.2425. And we do leave it as a 5 because the number next to the 5 is a 3. And because it's a 3, which is 4 and below, we leave the number alone. All right. Going ahead and getting the decimal for cosine, we get 8 divided by 2 times the square root of 17. Hitting enter. We have right here 0.9701. The number next to the 1 is a 4. So we need to go ahead and keep that 1, which means that our ratio as a decimal is 0.9701. All right, and the last one here, we actually don't even need the calculator. 2 divided by 8 simplifies into 1/4, which is the same thing as 0.25 or 25 cents. And there you have it. There are the ratios for sine, cosine, and tangent of angle Z as a decimal. All right, so here are the decimal answers for sine, cosine, and tangent of angle W. Notice how our decimals for sine and cosine are similar to the ones for sine and cosine of angle Z. It's just they swap places. All right, so now let's actually go ahead and have you try one on your own. All right, so pause the video here. See if you can give this one a try on your own. All right, so we're going to go ahead and we're going to check your answers in parts. So first of all, we had to solve for our missing side. So this is where we use the Pythagorean Theorem. A squared plus b squared is equal to c squared. Now our hypotenuse, as always, is our variable c. So when we substituted in, we simplified our square root and we got our answer to be 2 times the square root of 10 for our missing side. And then once we had our missing side, well, then it was just a matter of putting theta at one of your angles. So I went ahead and put theta right over here at angle V, labeled the triangle appropriately with hypotenuse, opposite, and adjacent. And then this is what we got for our sine of angle V, 3 divided by 7. And here's the decimal for that. Cosine of angle V is 2 times the square root of 10 divided by 7. And tangent of angle V is 3 divided by 2 times the square root of 10. All right, and then last but not least, go ahead and check your answer for sine, cosine, and tangent. But now it's for angle T instead. So your labels for opposite and adjacent had to change, and so did our ratios. All right, now let's actually go ahead and apply sine, cosine, and tangent to actually solve for one of these sides. So the problem says to use sine and cosine to solve for the values of each variable. And they want us to round the answers to the nearest tenths. All right, now I know they told us which trig ratios to use, but just for good practice, I'm going to go ahead and write down SO, CA, and TOA. All right, and since we are using sine, cosine, and tangent, we should probably go ahead and label our right triangle as well with hypotenuse, opposite, and here's the thing, with the opposite leg, our given angle is angle A, so across from that, or opposite to that, is BC, or the side that is labeled with X, which leaves us Y to be the adjacent side. All right, now this is what I meant earlier about figuring out what we're given, looking at what we're solving for, to decide which trig ratio to use. So let's go ahead and let's focus on solving first for X. All right, so just like the two words I highlighted earlier, we need to look at what we're given and we need to figure out which one are we solving for. So in our right triangle, I do realize that the angle is given, but I'm referring to the side. We're given the hypotenuse. So let's go ahead and write that down. It's 16, right? And then we are solving for x, which is the opposite side. So now we take a look at our three trig ratios, SO, CA, and TOA, to determine, okay, which one has both of the sides, opposite and hypotenuse. And it just so happens that SO is opposite divided by hypotenuse. So we're going to go ahead and use sine to solve for x. Okay, so let's go ahead and write down the ratio for sine. Sine of angle A will be equal to the opposite leg divided by the hypotenuse. Substituting all of our values in, we have sine of 49 degrees is equal to the opposite side, which was x, divided by the hypotenuse, which is 16. Now, we're going to go ahead and we're going to solve for x in the same way that we did for tangent. And the way we solved for any variable was we have a fraction on one side of the equation, and to get rid of a fraction, we need to multiply on both sides by the denominator. So in this particular case, 16 is in the denominator, so let's go ahead and multiply by 16 on both sides. So my 16s on the right side will cancel out, and on the left side I have 16 times sine of 49 degrees is equal to x. This part here is what we will put into a calculator, and I'll show you that in just a little bit. But let's go ahead and let's call it for right there. And then we're going to go ahead and we're going to now solve for y. So we're going to do the exact same thing. We need to always look at our given and figure out what are we solving for. The given is, of course, the same because of the same triangle, the hypotenuse. But now, because we're solving for y, y is the adjacent leg. And if I take a look at SO, CA, and TOA, the ratio, or the one that with the abbreviations that has both adjacent and hypotenuse would be CA. So this is cosine of the adjacent leg divided by the hypotenuse. Cosine of angle A is equal to the adjacent leg divided by the hypotenuse. So substituting in, we have cosine of 49 degrees is equal to y divided by 16. All right, so again, doing the exact same procedure to solve. Multiply on both sides by the denominator, 16. My 16s on the left side, or sorry, right side will cancel out. And then what I have left on the left side is 16 times cosine of 49 degrees is equal to y. And again, this is what we will put into the calculator. All right, so let's actually go ahead and put both of these expressions into the calculator. So first one says 16 times sine of 49 degrees. So let's go and type exactly that into the calculator. So 16 times sine of 49 degrees, closing my parentheses, we get about 12.1, rounded to the nearest tenths. That is our final answer for x. And for y, let's go ahead and let's do that same calculation again. The sine, cosine, and tangent buttons, just want to point that out, are right over here on the calculator on the left side. So we have 16 again, times cosine of 49 this time, closing my parentheses, we get just about 10.5. All right, so that right there is our x and y variables solved for using sine and cosine. Let me go ahead and zoom on out so that you can get the full picture of the notes from earlier in case you need it. And let's go ahead and let's have you try one on your own now. All right, so similar problem, but go ahead and pause the video here and give this one a try on your own. All right, go ahead and double check over your answers. So when we solved for A, our given side this time is our adjacent leg, and what we wanted was to solve for the hypotenuse, because that's A. So the only ratio that has both adjacent and hypotenuse is ca. So we substitute it in. And again, it doesn't matter that the denominator is a variable. I went ahead and multiplied by A on both sides, and it canceled out on the right side. And then it said A times cosine of 48. So because this is A being multiplied with cosine of 48, let's divide by cosine of 48 on both sides. Cancels out here. This we put into a calculator, and we get A is just about 14.9. And then, of course, for B, I know the problem says to use sine and cosine, but our given is our adjacent still. And to solve, because I'm looking for B, that's our opposite side. So it's actually probably a better idea to use tangent, which is opposite divided by adjacent. Substituting in and then putting it into a calculator, we get B is roughly 11.1. All right, so I think we covered just enough, but thank you very much for watching, and I'll see you in the next video.